Hi everyone, let's talk about finding the nth roots of a complex number. First, we need to precisely define what a root is. So we'll let n be in the positive integers. Then the nth root, or say nth roots of a complex number z will be the polynomial roots of f of x is equal to x to the n minus z. And notice that f of x is equal to 0 if and only if x to the n is equal to z. So we're taking a complex number x and taking it to the nth power, and we expect to get back z. And just to make things simpler, we're going to assume that z is not 0, because if it were 0, the only solution would be x equals to 0 by some simple arithmetic rules. So z is some point on the complex plane that is not the origin. Let's say it's a point up here, and we want to figure out what its roots are, its nth roots. Now, one idea is to set x equal to a plus bi and take it to the power of n and set that equal to z. But this is not a very easy method, because taking the power of the rectangular form is messy. So what we're going to do is we're going to use polar form instead. So the polar form will be, we're going to set z equals to r e to the I theta, and we're going to say that x is equal to s e to the I phi. So that's going to be the nth root, or just a general way of representing the nth roots. So if we plug this into the equation, x to the n is equal to z, then we get, by working backwards, that s e to the I phi to the power of n is equal to r e to the I theta. And working backwards more, we get s to the n is equal to e to the s to the n times e to the I n phi is equal to r e to the I theta. And what we get is that this is true if and only if s to the n is equal to r, and we have to have that n phi is congruent to theta mod 2 pi. So what that means is, like, we go around the circle several times if needed, and this is equivalent to n phi is equal to theta plus 2 pi k for some integer k. So the first one is easy to deal with. S and R are both positive, since we're not taking the root of a 0 complex number. So S is simply equal to the nth real root of R. But it's the second one that's more interesting. We find that phi is equal to theta plus 2 pi k over n. So it seems like there would be a phi for every integer k, but there might be overlaps. So we'll start with this idea, but we want to see when these give rise to the same complex number. And these give rise to the same complex number if and only if s e to the I theta plus 2 pi k1, some integer k1, over n 2 pi k1 over n is equal to s e to the I theta plus 2 pi k2 over n. And the s's cancel out, and this is true if and only if theta plus 2 pi k1 over n is equal to theta plus 2 pi k2 over n plus 2 pi j for some j in the integers. So now we're just going to work with this equation. Let's clear the denominators. We get theta plus 2 pi k1 is equal to theta plus 2 pi k2 plus 2 pi n. The thetas cancel out, and then we can divide out by 2 pi overall. So we get k1 is equal to k2 plus nj. And that is true if and only if k1 is congruent to k2 mod n. So let's look at the solutions. Our solutions are of this form. The angle is of this form. So we get that x is equal to s e to the I phi, which is equal to the nth root of r times e to the I theta plus 2 pi k over n for, and this is the key part, k equals to 0, 1, 2, all the way through to n minus 1, because those are the residues, the least residues modulo n. So there are n solutions. So there are nth roots of a non-zero complex number. So that takes care of that, but I want to make an observation. Let's say we're going to call this wk. So we have n plus 1 of these, and we have w0, w1, w2, all the way through to wn minus 1, and we're also going to write wn is equal to w0, just so that we cycle all the way around. I want you to notice that wk plus 1 over wk is equal to the nth root of r over the nth root of r times e to the I theta plus 2 pi k plus 1 over n e to the I theta 2 pi k over n. And if you simplify this, you get rid of these, and you get e to the I, the thetas cancel out, and the k's cancel out, and what we're left with is e to the I times 2 pi over n. So when we're going from w0 to w1 and then to w2 all the way through to wn minus 1 and then back to w0, we're just doing rotations by 2 pi over n radians. So what we have is that the roots they form the vertices of a regular polygon. Like these three are the third roots of unity, meaning of 1. If we want to do the fourth roots of unity, we find that one of them is here, one of them is here, one of them is here, and the last one is here. And these are the fourth roots of unity. So for the roots of unity, we always start with this point, which is 1, 0, and then we rotate around until we get back there. And we keep rotating by increments of 2 pi over n radians. The difference with finding the root of a different complex number is that the first one might not be over here, it might be somewhere else. Okay, thank you for watching, and I'll see you next time.